What if I told you the universe has a baby picture? Not a painting, not a simulation, but an actual photograph of the cosmos when it was just 380,000 years old. And no, you don't need a time machine to see it. You just have to tune into the faintest, coldest glow that fills the universe, the cosmic microwave background radiation. Today, we're going to peel back its secrets, and trust me, they're mind-blowing. Hey everyone, welcome back. Today, we're diving deep into one of the most fascinating discoveries in all of science, the cosmic microwave background, or CMB for short. This isn't just some obscure physics trivia. It's literally the oldest light we can see in the universe. Hidden in that glow are clues about where we came from, how the universe began, and maybe even hints about its ultimate fate. So grab a coffee, or maybe something stronger, because we're about to time travel. Not with a DeLorean, but with photons that have been traveling for nearly 14 billion years. Let's rewind the cosmic clock. Imagine the universe right after the Big Bang. At first, everything was unimaginably hot and dense. Think of a soup, but instead of noodles and broth, it's made of pure energy, subatomic particles, and light bouncing around like crazy. For the first few 100,000 years, the universe was opaque. Completely foggy. Photons, the particles of light, couldn't travel freely. Every time they tried, they were scattered by electrons and protons. If you could somehow stand inside that early universe, you wouldn't see stars, or galaxies, or even black space. You'd just be surrounded by a blinding, glowing plasma mist. But as the universe expanded, it also cooled down. By about 380,000 years after the Big Bang, things reached a turning point. The plasma thinned out enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, light could travel freely for the very first time. That moment is called recombination, and the light released then is what we now see as the cosmic microwave background radiation. Now, fast forward almost 14 billion years later to the 1960s. Two engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were working with a big horn-shaped radio antenna. They were just trying to get rid of some annoying background noise in their measurements. They cleaned the antenna. They chased away pigeons nesting inside it. They tried everything. But no matter what, there was this stubborn hiss, like static, that just wouldn't go away. What they didn't realize at first was that the hiss wasn't a mistake. It was the universe itself whispering its oldest story. They had accidentally discovered the cosmic microwave background. Meanwhile, just across town, a group of physicists at Princeton had been working on a theory predicting exactly this kind of signal. When they heard about Penzias and Wilson's discovery, they realized, this was it. The smoking gun of the Big Bang. That discovery won the Nobel Prize and changed cosmology forever. So, what does the CMB actually look like? If you could see it with your eyes, the whole sky would glow faintly in microwaves. But to human eyes, it's invisible. Scientists had to build special detectors to map it. At first, it looked almost perfectly uniform, like a flat, featureless glow. But then, more sensitive satellites like COBE, WMAP, and Planck revealed that the CMB isn't perfectly smooth. It has tiny temperature fluctuations, only about 1 part in 100,000. Picture a speckled pattern, like a heat map of the sky. These tiny ripples aren't random noise. They're the seeds of everything. Galaxies, stars, planets, even us. Those little differences in temperature eventually grew, under gravity, into the cosmic structures we see today. In other words, the CMB isn't just a baby picture. It's a baby picture with freckles that tell us how the universe grew up. So what secrets does the CMB hold? Let's break down a few of the biggest ones. First, the age of the universe. By measuring the CMB, scientists can calculate the exact rate of expansion. Today, we estimate the universe is 13.8 billion years old, and the CMB is one of the main reasons we know that number so precisely. Second, the ingredients of the cosmos. The CMB also tells us what the universe is made of. Not just matter, but dark matter and dark energy. Thanks to the CMB, we know that normal matter, the stuff that makes up stars, planets, and us, is less than 5% of the universe. The rest is invisible. Third, evidence for inflation. The CMB carries whispers of what happened in the first trillionth of a second after the Big Bang. That's the theory of cosmic inflation, which suggests the universe expanded faster than the speed of light for a brief instant. The pattern of fluctuations in the CMB lines up beautifully with this idea. And fourth, the geometry of the universe. The CMB lets us measure the universe's shape. Spoiler, it's flat. Not flat like a piece of paper, but flat in the sense that parallel lines in space don't curve together or apart on the largest scales. That has huge implications for the fate of the cosmos. Now here's the twist. Even though the CMB has revealed so much, it also raises new mysteries. Scientists have noticed some strange anomalies in the data, like the so-called cold spot, a region of the CMB that's unexpectedly chilly. Nobody's quite sure why it's there. Could it be a statistical fluke? Or maybe evidence of something exotic, like another universe brushing up against ours? There are also questions about whether the CMB can help us detect primordial gravitational waves, ripples in spacetime created right after the Big Bang. If we could spot those patterns hidden in the CMB, it would be like seeing the very first tremors of creation itself. So while the CMB is incredibly well studied, it still holds puzzles that could change our understanding of everything. Let's pause for a second and just appreciate how wild this is. Think about it. Photons that left atoms nearly 14 billion years ago are still traveling through space, and some of them are hitting detectors on Earth, telling us their story. It's like receiving a postcard from the dawn of time. And it all started with a couple of engineers scratching their heads over a stubborn hiss in their radio antenna. To me, the CMB is a reminder of human curiosity at its best. We asked where we came from, we looked up, and the universe gave us an answer. Not just in poetry or philosophy, but in actual measurable data, encoded in a faint glow that surrounds us all. So, what is the cosmic microwave background radiation? It's the oldest light in the universe. It's the afterglow of the Big Bang. It's a cosmic fingerprint that tells us how old the universe is, what it's made of, and how it evolved. And even today, it's still full of secrets waiting to be unlocked. Whenever I think about the CMB, I'm struck by this. The universe isn't silent. It's been humming its tune since the very beginning, and we're just now learning how to listen. If you enjoyed this journey into the universe's oldest light, don't forget to hit that like button. It helps more curious minds find this video. And hey, drop a comment. What blows your mind most about the CMB? That it's a baby picture of the universe? That it proves the Big Bang? Or maybe the idea that it might even hint at other universes? Subscribe if you want more cosmic storytelling, because we've only scratched the surface of the universe's mysteries. Until next time, keep looking up, because the universe has been shining its story at us for nearly 14 billion years.